Welcome to the deep dive. Today we're exploring something pretty wild. How your sense of touch isn't just passively reporting what's out there, it's actively shaping your perception, and sometimes it even gets tricked.
Yeah, it's fascinating stuff.
You know the visual waterfall illusion? You stare at downward moving water, look away, and static things seem to drift up. It's like your brain's motion detectors get fatigued and then, overcorrect.
Right, a classic adaptation effect.
But what if that kind of adaptation happens with touch? Can feeling one thing change how you feel the next thing?
That's exactly the question.
We're diving into a deep, fascinating piece from Scholarpedia on after effects in touch. And our source material says, yes, absolutely, this happens with touch. And it's not just temperature, like that old trick.
The hot and cold water hands.
Yeah, exactly. Put one hand in hot, one in cold, then both in lukewarm. No, this goes way beyond that. It affects how we perceive size, shape, curvature, motion, vibration, roughness, even weight.
That's right. So the mission for this deep dive is really to unpack the source material piece by piece and reveal these surprising ways our tactile perception is, well, dynamically influenced by what we've just felt.
Okay.
We'll look at specific experiments and what they tell us about the complex way our brains actually process touch.
And this isn't even a new idea, is it? It goes way back. The source mentions the 17th century.
All the way back. Let's start there. What did philosopher John Locke notice that kind of hinted at all this?
Okay, Locke, what was his observation?
Well, John Locke, in his essay concerning human understanding, he used this classic thought experiment. Imagine you have 3 buckets of water, one cold, one warm, and one lukewarm in the middle.
Right.
You place one hand in the cold water, the other in the warm water for a bit.
Yeah.
Then you plunge both hands into the lukewarm water. What happens?
I think I know this one. The hand that was in the cold water feels the lukewarm water as warm, right? And the hand that was in the warm water feels that same lukewarm water as cold.
Exactly. It's a simple, elegant demonstration. An early sort of intuitive observation of a temperature after effect in touch. You adapt to one temperature, and it shifts your perception of the next one.
Okay, so Locke described it. Did anyone actually take that idea and test it formally?
They did, yeah. Arnold and colleagues replicated this specific temperature experiment with both adults and, interestingly, children.
Did it work?
Oh yeah, they confirmed the after effect of both groups. But what's fascinating is that roughly half the children genuinely believed the water was actually different temperatures for each hand.
Really? They thought the water itself changed.
Yeah, they expected that if they rotated the bucket, the feeling would switch hands. Adults, on the other hand, were much more likely to understand that there was a difference in their feeling, their perception, not the water itself.
Huh. That hints early on that the subjective experience is really key here, doesn't it?
Absolutely. It's about how things feel, not necessarily how they are objectively.
So the source makes it clear this goes way beyond just temperature. Let's move through the list. Tactile qualities that show these after effects. How does it work for size?
Right, the tactile size after effect. Studies like those by Walker and Shea. They had participants touch and judge the width or length of bars.
Okay.
After they'd explored, say, a wide bar placed at a specific location on their hand, a subsequent identical bar felt narrower at that same location.
And the reverse. Adapting to narrow makes it feel wider.
Exactly. And because it depended on the location, they termed it a contingent after effect.
Gotcha. And this worked for 3D objects too, not just bars, like spheres.
Yes, similar experiments were done with spheres. Uznazia famously had people repeatedly grasp a small sphere in one hand and a large sphere in the other. Then they were given identical intermediate-sized spheres, one in each hand.
Let me guess. The identical sphere felt smaller in the hand that had held the large one and larger in the hand that had held the small one.
Precisely. And Kappers and Bergman-Tiest, they formalized these experiments. They found the perceived size difference between the two identical spheres could be quite significant.
How significant?
As much as 24% of the test sphere's actual size, which is pretty substantial. They also showed that this worked for other shapes too, like tetrahedra.
Okay, here's where it gets really interesting, I thought. Did any of these studies hint at where in the processing stream this size after effect might be happening? Is it skin? Is it brain?
Well, what's truly revealing is a study by Maravita. It involved a patient with right brain damage.
Okay.
Now, this patient had a condition. They didn't consciously perceive a sphere that was placed in their left hand. You could put it there, they wouldn't report feeling it, wouldn't be aware of it.
Wow, okay, so blind sight but for touch.
Something like that, yeah, haptic neglect, essentially. But here's the kicker. When they then felt an identical test sphere in their right hand, the hand they could feel with Consciously, its perceived size was still influenced by the size of the sphere that had been placed in their left hand, the one they weren't consciously aware of.
Wait, hang on. So even if they didn't feel it consciously, their brain was still processing that touch information enough to mess with their next perception?
Exactly. It's incredible evidence. It shows that somatosensory information is being processed by the brain at some level, even without conscious perception. And that unconscious processing can still drive the after effect.
That's wild. And those sphere and tetrahedral studies also suggested something similar, didn't they? You mentioned they found the after effect was much smaller, or maybe didn't happen at all, if you adapted to one shape, like a sphere, and then tested with a different shape, like a tetrahedron.
Yes, that's a crucial point. That led them to suggest calling it more accurately a size-shape after effect. Right. The fact that the after effect depends on the shape implies that the adaptation isn't just happening at some basic level of feeling something in your hand. It means the processing of the object shape is involved.
Which points to?
Which points towards higher processing areas in the brain, right? Not just the simple nerve endings in your skin. It has to involve areas that understand shape.
Fascinating. So it's not just size in isolation, but size and shape together. And processing happens even without conscious awareness. Okay, let's move on. Curvature. Gibson's 1933 study on this sounds like a classic.
It really is. Gibson had blindfolded participants run their fingers over a convex curve like the outside of a bowl for a few minutes.
Okay, adapting to the curve.
Right. After that adaptation, they were asked to touch a perfectly straight edge.
And the straight edge felt curved in the opposite direction, concave.
Precisely. They consistently reported the straight edge felt concave. This showed a clear kinesthetic curvature after effect, an after effect based on the movement and feeling of tracing that curve. They also noted that the convex curve itself started to feel less curved during the adaptation.
Right, the adaptation itself. Makes sense. Now, Vogels and colleagues did more detailed studies with 3D shapes, is that right?
They did, yeah, using solid 3D objects. They found significant curvature after effects even after very short adaptation times.
How short?
As little as 5 seconds was enough to start seeing the effect. It grew and peaked around 10 seconds of adaptation, and it could last for a surprisingly long time. It was still significant even after 40 seconds of just waiting.
Wow.
And they also showed if you touched multiple surfaces in a row, say convex and then concave, then a test surface, the perception of that final surface was influenced by the curvatures of both the first and second surfaces.
So the effects can stack up or interact, which brings us back to that core question. Where are these after effects actually happening? Is it just fatigue in the skin receptors or something deeper, more central in the brain?
That's the crucial question everyone wants to answer. Vogels et al. Looked into this initially. They found that the rate at which the after effect faded away, its decay rate, didn't really change much whether you held your hand still or made a fist or wiggled your fingers between adapting and testing.
So messing with the hand locally didn't speed up recovery.
Right. Which suggested that simple fatigue of the nerve endings in the skin probably played, at most, a minor role. Now, in their specific setup, which used static touch, they also didn't find a transfer of the after effect to the other hand.
Which might suggest it wasn't highly central.
Initially, maybe.
Yeah.
But later studies really contradicted that idea, especially when looking beyond just static touch.
Okay, so what did they find?
Van der Horst and colleagues provided really compelling evidence for central processing. First, they showed a curvature after effect, even when participants used simple static finger touch, no movement involved. And here's the big thing. They found a partial, but definitely significant, transfer of the effect between fingers,
Okay.
including fingers on different hands.
Transferring between hands, that sounds like it has to be brain processing, not just the local skin effect.
Exactly. That finding strongly suggested a high central level origin, very likely happening somewhere in the somatosensory cortex, the main brain region that processes touch information.
Makes sense. What about more natural touch, like when we actually move our hands?
Right, dynamic touch, they looked at that too. They compared actively moving your fingers over a surface versus having the surface move under a static finger.
Active versus passive exploration.
Exactly. Both active and passive dynamic touch produced after effects, but this time there was full transfer of the effect to the other hand.
Full transfer.
Yeah. Which really solidified the idea of a high-level origin, at least for these dynamically obtained after effects. And interestingly, the active condition where you were actively moving and exploring resulted in a substantially larger after effect.
So the kinesthetic information, that sense of your own movement, actually adds to the effect, boosts it.
It seems so. It shows that the representation being adapted, the thing that's getting tired in the brain, depends on your mode of exploration, and that kinesthetic input is important.
And even touching with a tool, did that show transfer?
Yes, Denisova and colleagues used virtual stimuli and had people touch with a tool. They found both the after effect and a partial transfer to the other hand during dynamic touch, again reinforcing the major role of that movement information in where this effect originates.
Okay, let's broaden the idea of shape perception beyond just size and curvature. The source mentions a tactile face after effect, like similar to the visual one where you stare at one face and a neutral face looks different.
Exactly. This is a fascinating study by Matsumiya that really highlights high-level processing in touch. Participants used their hands haptically, explored these face masks designed with different expressions: sad, happy, or neutral.
Okay.
After adapting by feeling, say, a happy face for about 20 seconds, they were asked to judge the expression of a neutral face mask just by touch.
And what did they perceive that neutral face as?
Well, after adapting to the happy face, participants were overwhelmingly likely to perceive the neutral face as sad. The data showed something like 90% of the time.
90%, wow.
Yeah. But after adapting to the sad face, they were much less likely to perceive the neutral face as sad, closer to 35%, compared to maybe 50% when they hadn't adapted at all.
That's a huge shift in perception. So adapting to happy makes neutral feel sad. Adapting to sad makes neutral feel less sad, or maybe more neutral happy.
Exactly. It's powerful evidence that the adaptation is happening at a level where tactile facial expressions are being processed. Not just bumps and curves, but the meaning of those shapes as a face.
And the proposed brain area for this is where you'd expect complex touch and facial processing to happen.
Precisely. The proposed origin is in higher cortical areas known to process haptic facial information places, like the inferior frontal gyrus, inferior parietal lobe, and the superior temporal sulcus. Again, it points to complex, high-level brain areas being involved in these tactile shifts.
So even something as complex as facial expression and touch can show these after effects originating high up in the brain. Okay, what about motion? Feeling something move across your skin, does that create an after effect?
The tactile motion after effect, or TMAE, yes, it does exist, but the source notes it's been historically much harder to induce and less consistent than the visual waterfall illusion.
Oh, why is that?
Well, early studies had kind of mixed results. Some didn't find it reliably. Others only found it in about half of their participants. And sometimes the perceived direction of the after effect wasn't even the expected opposite direction. Sometimes it was the same direction or just other.
Huh. Not as clean as the visual one, then.
Not initially. However, Watanabe and colleagues did manage to elicit more robust, opposite direction tactile motion after effects. They used specific vibrating pin stimuli, carefully designed to stimulate the right mechanoreceptors, those nerve endings sensitive to pressure and vibration in just the right way.
So the stimulus matters a lot.
It seems so. And Kuraki et al. Found the perceived direction of the after effects seemed based on the environment the motion occurred in, not just where it physically was on the skin. They suggested that while the peripheral receptors in your skin are still essential inputs, the processing involves some kind of higher-level remapping of direction.
Interesting. And did the speed of the original motion matter? Like, did faster movement cause a stronger after effect?
Yes. Planeta and Servos found that the duration, frequency, and even the reported vividness of the tactile motion after effect all increased with the speed of the adapting stimulus. And by stimulating different body sites, they concluded that certain fast-responding nerve endings, the fast-adapting type I receptors, and also hair follicles, were most likely involved in processing that initial motion stimulus.
Okay, so that's the after effect of perceived motion direction. But the source also mentions a tactile speed after effect, separate from direction.
That's right, the tactile speed after effect, studied by McIntyre and colleagues. After adapting to a stimulus moving at a certain speed, a subsequent test stimulus moving at a standard speed feels like it's moving slower, compared to feeling it with a hand that hasn't been adapted.
So adaptation makes things feel slower.
Correct. But, crucially, they found this effect was independent of the direction of the adapting stimulus relative to the test stimulus. It didn't matter if they moved in the same direction, opposite directions, whatever.
Why is that crucial? What does the direction independence tell us?
Because the nerve endings in your skin that detect motion, the peripheral afferents, are sensitive to direction. They fire differently depending on which way something moves across them. So if the after effect depended strongly on the relative directions, it might suggest processing happening right there at the skin level, linked to those direction-sensitive receptors. But since the speed after effect doesn't care about direction.
It suggests the adaptation is happening after direction information has already been processed or integrated.
Exactly. It strongly suggests the adaptation is occurring centrally in the brain, not peripherally at the receptor level.
Very clever distinction. Okay, let's shift gears again. Vibration. Can prolonged exposure to vibration change how you feel subsequent vibrations, like on your phone, maybe?
Absolutely. Letterman and colleagues had participants adapt to vibration at specific frequencies, say 20 hertz or 250 hertz, for about 10 minutes.
Okay.
Afterwards, their perception of the intensity of subsequent vibrating test stimuli was significantly decreased. They felt less intense.
And did the frequency matter?
Yes, this reduction was strongest for test stimuli vibrating at the same frequency as the adaptation. And if they adapted at 250 hertz, very low-intensity test stimuli at that frequency became completely undetectable afterwards. They just couldn't feel them anymore.
Wow. So you adapt specifically to that frequency. Did this tell them anything about roughness perception? Because vibration is linked to how we feel textures, right?
Well, initially, this Letterman study suggested that maybe the sense of vibration and the sense of roughness were processed separately. Because adapting to vibration didn't seem to influence overall roughness perception in their experiment.
Okay, but
Collins et al. Later found that vibration adaptation does impair your ability to discriminate between very fine textures.
so it affects fine textures specifically.
Exactly, suggesting that certain receptors, like poscinion receptors, which are really good at sensing high-frequency vibration, do play a specific role in our perception of fine roughness. So there is a link there.
Got it. And does the duration of the vibration adaptation matter a lot? Like, does vibrating for longer make the effect stronger?
Yes, Hahn showed that quite clearly. Longer adaptation periods lead to stronger after effects. He found that even after 25 minutes of continuous adaptation, the strength of the effect was still increasing.
Still going up after 25 minutes.
Yep, and it took a full 10 minutes to recover afterwards. So it's a pretty persistent effect once you induce it strongly.
Okay, what about roughness itself? If I rub, say, sandpaper for a while, does the next surface I touch feel different?
Yes, definitely. Karamanowicz and colleagues showed a clear roughness after effect. After scanning a rough surface with your hand, a subsequent surface feels smoother than it actually is.
Okay, rough makes things feel smoother. What about adapting to smooth?
And conversely, after scanning a smooth surface, the next surface feels rougher than it is.
Wait, that's fascinating. Adapting to smooth made things feel rougher, while adapting to rough made them feel smoother. It's an opposite shift, depending on what you adapted to.
That opposite directionality is a key point the authors made. They argue this pattern isn't really consistent with simple overstimulation or fatigue of the peripheral receptors in the skin.
Why not?
Well, if it were just fatigue, you might expect adapting to both rough and smooth to shift perception in the same direction, right? Maybe just to different degrees, like both make things feel smoother, just rough makes it feel much smoother.
Yeah, that makes sense.
The fact that they shift perception in opposite directions strongly suggests the adaptation is happening at a higher processing level, probably in the somatosensory cortex, where complex tactile features like roughness are integrated and interpreted.
Another pointer towards central processing. Okay, finally, let's talk about weight. Is there a weight after effect? If I hold something heavy, does something else feel lighter?
Yes. Di Mendoza demonstrated what he termed the gravimetric after effect. Gravimetric meaning related to weight or gravity.
Okay, how did that work?
In a series of comparisons, if participants first held two weights that differed substantially, say, a heavy one in their left hand and a light one in their right for a bit, and then they're presented with two identical weights.
The identical weight in the hand that held the heavy one felt
lighter. It was perceived as lighter than the identical weight in the other hand, which had held the light weight.
The size-weight illusion is related, but this is purely from prior holding, right?
This is specifically an after effect of holding the different weights beforehand. Di Mendoza called it graphometric because it wasn't entirely clear if it was solely about touch or also involved proprioception, or sense of limb position, and kinesthesis, your sense of movement. It's likely a combination.
Right. Okay, so we've covered a lot. We've seen compelling evidence for after effects in temperature, size, curvature, shape, like faces, motion direction, motion speed, vibration, roughness, and weight. That's pretty much all the main aspects of touch, isn't it?
It covers a huge range, yeah.
And for many of these, maybe most, the evidence, things like transfer between hands or direction independence for speed or the opposite effects for roughness, strongly points away from just simple peripheral fatigue. It points towards complex processing higher up in the brain.
That's really the critical takeaway from much of this research. Touch isn't just a raw signal coming directly from your skin. It's actively processed, interpreted, and crucially, recalibrated by the brain based on recent history.
Okay, so if we connect this to the bigger picture, several of these after effects you mentioned, motion, curvature, face perception, they also exist very clearly in vision. We know about visual after effects for these things.
Right. The parallels are striking.
Does this mean the brain areas processing touch for these features might overlap with those processing vision? Are they shared?
That's the really intriguing cross-modal question. And the source highlights studies that look directly at this. Conkle and colleagues, for instance, tested this specifically for motion.
What did they find? Could adapting one sense actually influence the other?
Absolutely, yes. They found that adapting to a visually moving stimulus, just watching something move, could induce a tactile motion after effect on your skin.
Watching motion makes your skin feel motion later.
Yeah, in the opposite direction, just like the visual motion after effect. And perhaps even more surprisingly, adapting to tactile motion, feeling something move on your skin, could induce a visual motion after effect when you looked at something static afterwards.
Wow, so feeling something move on your skin can literally make something you see afterwards look like it's moving in the opposite direction.
That's what they found. It's incredibly powerful evidence that the processing of visual and tactile motion must require at least partially overlapping brain areas. It suggests the brain isn't keeping these senses in entirely separate boxes when it comes to motion processing.
That really blurs the lines between senses.
It does. Conkle and Moore further suggest that while there's overlap, the specific origin of the after effect can still vary depending on the complexity and type of processing involved. Some might be more sensory-specific, others more abstract and multimodal.
And Matsumiya, who did the tactile face study, found similar cross-modal transfer for face after effects, too.
He did. The face after effects he found in touch, feeling the masks, and the ones in vision transferred bidirectionally.
Meaning?
Meaning adapting to a visual face changed how you subsequently felt a haptic face mask. And adapting by feeling a haptic face mask changed how you subsequently perceived a visual face.
So seeing a sad face could make a neutral mask feel happier, and feeling a sad mask could make a neutral face look happier.
Essentially, yes. It biased perception in the opposite direction across senses. Again, this strongly indicates shared brain representations for face processing at some level across both touch and vision. It's not just seeing faces or feeling faces in isolation, it's the abstract concept of face expression being processed in areas accessible to both senses.
Okay, so what does all of this really tell us? What's the big picture takeaway from this deep dive into tactile after effects?
I think it fundamentally tells us that our sense of touch is far more dynamic, far more constructive, and less literal than we might intuitively assume. It's not just a passive reporting system relaying signals from the skin. It's constantly adjusting and recalibrating itself based on our recent sensory experience. And crucially, these adjustments, for many tactile qualities, aren't just simple fatigue happening out at the periphery in the skin. They involve complex processing deep within the brain.
And sometimes that processing happens in areas shared with other senses, like vision.
Exactly, which underscores how incredibly adaptable and interconnected our sensory systems truly are. They're not working in isolation.
Yeah, this deep dive has really hammered home just how plastic and, well, adaptable our sense of touch is. It's not just about the nerve endings in your fingertips reacting. It's about the brain actively making sense of that input and being profoundly influenced by everything you've just felt.
Indeed. And the evidence showing these effects originate in higher brain areas and can even cross over between senses. That really challenges the common sense idea that touch is purely a peripheral sensation tied only to our skin receptors. It's much more integrated than that.
It really makes you think if our perception of seemingly basic things like size or curvature or even the expression on face we touch can be shifted just by what we've recently experienced. And this processing happens in complex brain areas, sometimes shared with vision. What does that imply about how our brain constructs our entire perception of the world around us?
That's the big question, isn't it? This line of research really makes you ponder how much of our perceived reality is a straightforward, objective reading of sensory input, and how much is actively built, shaped, contextualized, and sometimes even, well, tricked by the brain, influenced by our recent sensory history across all our senses. It suggests perception is much more of an active construction project than a passive recording.